Alrighty, so our group was assigned particle in the box model. So we're going to talk about the Schrodinger equation, wave functions, and normalization. So you probably remember this graphic from the beginning of Unit 2. So it's essentially outlining a particle in the box model. It's showing if we have a boundary at 0 and L, there's a 100% chance of finding the particle somewhere within these bounds. It can't be on the wall or outside of the wall. It has to be within the well area. And this is really important, especially for determining different probabilities. Say if the particle was between 0.5 and L instead, what's the probability? And we'll do an example talking about that in our normalization section. So for kind of an overview of what we're going to do through this lecture, we have a particle in the box overview, then followed by the Schrodinger equation, wave functions and probability density, talk about normalization, and then quantized energy states, and kind of a wrap up of just why the particle in the box is important. So we really hope this is helpful and it helps you study for the unit exam too.
The particle in a box model is a model of translational motion that is used to describe the behavior of a particle in a confined space. It has several applications, but one example is an electron within a conjugated carbon chain, where the electron is able to move along the conjugated molecule due to delocalization. In our example, the electron can exist anywhere along the conjugated carbon chain, which is denoted by 0 to L. Any particle in this model can only exist between 0 and L. We can show this rule mathematically by saying that the potential of the particle is infinity outside of the well and 0 inside of the well, because objects will move toward lower potential. So the particle is confined within the well where potential equals 0. In our example, the boundaries of the well could represent nodes or the end of the conjugated chain. Using the Schrodinger equation and the constraints of the particle in a box model, we can find the probability density of the particle within the well and the particle's allowed energy states. This will help us to better understand the wave-like behavior of a particle and why energy levels are quantized in confined spaces. The Schrodinger equation tells us about the wave function of a particle. By applying the conditions of the particle in a box model to the Schrodinger equation, we get an equation for the wave function of a confined particle. This equation satisfies the conditions of the particle in a box model because for any value of x, which is outside of the well, psi of x equals 0, signifying that the particle does not ever exist there. But within the well, each value of n gives a different wave function.
Alright, so the next concept that we're going to be covering is something called a wave function, and we're going to be discussing how that's related to figuring out where a particle might be in space. So first and foremost, a wave function is essentially something that describes a particle's quantum state in an isolated system. So it's going to give us a really good idea of like a model or a representation of a given wave from an equation. It's often going to be represented by the Greek letter psi, so you'll see that symbol kind of used throughout the rest of the lesson today. For a lot of different models, a wave function is going to be something kind of resembling a sine of x function. For the purposes of our particle in a box model today, we're going to be using this specific equation. So the wave function is equal to a times the sine of n pi x over L, where n is the quantum number. Now it is important to note that wave functions are not directly observable, so we can't actually directly measure anything from a wave function. So it's not going to give us a lot of really useful information about the location of a particle on its own. However, there are some really cool ways that we can manipulate wave functions to use them to figure out something about that particle. So if you take the wave function of a particle and square that equation, you can actually find the probability of locating that particle within a really small volume or a small set of coordinate values. And that's going to be something called your probability density. Now, for example, today, that small volume is essentially going to be kind of related to the confines of our imaginary box that the particle resides in. So the probability density is equal to the wave function squared. In order for the wave function to be fully consistent with this concept of probability density, it's got to conform to a couple different conditions. So within the confines of your box, so these two kind of outer limits here, the wave function has to be continuous, finite, and single valued. And as long as it meets all of those criteria in between those two endpoints, you're good to go. Another thing of note, that anywhere that the probability density is equal to 0, that's going to be something referred to as a node. And that's basically just a space or a region where there is absolutely 0 probability of ever finding that particle in that region. So anywhere that the regular wave function is going to cross this axis here is where you'll get a node, as well as the 2 endpoints. So you're never going to find the particle at any of those 4 positions. All right, so here's a practice problem to help you kind of get comfortable with this idea of wave functions versus probability density. So you're given a wave function defined as this equation, and it's asking you to kind of sketch and interpret drawings of both the wave function and primarily probability density. So I'll give you a second to do it on your own, and then I'll kind of walk you through the steps and what we're looking for here. All right, so the first thing I want to start with is sketching the general graph or the function of the regular wave function. So your wave function is going to look something like this. And it's going to be within your confines of 0 to L. So this L, which is also equal to 1. So this is going to be your wave function. But like I said before, it's not really telling you anything specific about the location of that particle. So if you were to essentially square this equation to get the probability density, you're going to instead find a graph like something a little bit more like this. And this is still going to be L equals 1, and this will still be 0. So there are a couple things of note here. First and foremost, I want to highlight some of the nodes. So every point where our wave function crosses this axis, or our probability function touches the axis, those are each going to be a node where there is absolutely no chance of your particle being found there. So that's going to be L over 2 here. That's a node. But then you can see where these peaks are the highest, that's where you're going to have the highest probability of finding a particle in that space. So essentially here and here is going to be your highest probability. So that's going to be 3/4 of L and also 1/4 L. And on this next page, there's just kind of a cleaner drawing explaining exactly what I just stated. So you have your regular wave function, your probability density function, and then also a comparison of both those functions together.
Alrighty, so I'm going to cover normalization within the particle in the box. So why is normalization necessary? First, it ensures the integral of the square of the wave function over all space equals 1. So this is just what it's showing. That square of this wave function is equal to 1, which is going to come into play in part 2 here. So square of the wave function's amplitude represents probability density of finding a particle at a specific location. So we know that the wave function is directly proportional to our probability. So then our wave function squared is going to be directly proportional to p squared, which is going to be our probability density. And then through normalization, we guarantee the total probability of finding a particle within the box is equal to 1. So if we have our box here, x equals 0, x equals 1, it could be also in terms of L. The probability of finding a particle somewhere within is equal to 1, which is going to be important for probability calculation. So normalization essentially ensures that the wave function's squared magnitude, or the probability density, integrates to 1, meaning that there's a 100% chance of finding the particle somewhere within that range given. So this is really crucial for probabilistic interpretation of wave function, and ensures that your calculated probabilities, like we'll see in an example, are physically meaningful and you can find a value. So breaking normalization into steps, this is just kind of for you to go back and look at if you want to kind of visually see the steps. But we're going to go ahead and work on an example. So normalize the wave function given in the problem here of the range x equals 0 to x equals 1. So we have our wave function x equals sine pi x over 2. and we're looking from x equals 0 to x equals 1. So we're going to go and take the integral from 0 to 1 of sine squared pi x over 2 dx. And then remember, we're given the integration, so we can just look up the integration table for this. We're also going to take this pi over 2 and make it a constant b. Just going to simplify our work. We're not going to have to write pi over 2 after everything. So the integration of this is x over 2 plus 1 over 4b times the sine of 2bx evaluated from 0 to 1, which is the range we're given. So now we can set it equal to 1. That wave function squared, as we talked about earlier, is equal to our probability density squared, which is going to be 1 in this case. So 1 equals some normalization. And now we're just plugging in. So we're plugging in x is equal to 1 for this first part. 1 over 2 minus 1 over 2 pi sine of 2 pi times 1 over 2. Now we're plugging in x equals 0, 0 over 2 minus 1 over 2 pi sine 2 pi over 2 times 0. So you can plug that. There we go. Okay, so now we're just simplifying it further before we put in our calculator. 1 equals n squared times 1/2 minus 1 over 2 pi sine of pi, which is going to equal 0. It's important to know those trig rules. And we get 1 equals n squared times 1/2. So now we're just going to divide by 1/2 on both sides. So we get 2 equals n squared, square root of that, square root. So our normalization equals the square root of 2. So now we can plug it back in at the top. And we have the wave function of x equals the square root of 2 sine of pi x over 2. So now we can take this wave function that we have and bring it down here. So now if we want to use this wave function and find the probability the particle is between x equals 0.5 and x equals 1, so now the probability is not equal to 1 because it's not the whole box that we're talking about. We're now thinking, okay, what about just from this range? X is 0.5 to 1. So what's the probability that a particle is within here? And now that we've normalized our function, we can actually have meaningful calculations. So look in the slides for the solution to this problem, as well as another practice problem of just normalization that you should definitely do if you want more practice.
Hi, I'll be wrapping up today's lecture by briefly explaining what quantized energy are and why they are important to the particle in the box model. In quantum mechanics, energy is quantized, which means energy is not continuous. It comes in set of amount. Think of it like climbing stairs. You can stand on one step or the next, but not in between. Electrons in an atom can only exist in certain energy level, not anywhere they want. When electrons gain energy, they jump to a higher level. When they drop back down, they give off energy usually like light. This is how atoms produce specific color of light like neon signs or fireworks. When particles in the box model, the allowed energy level are based on wave function. The higher the quantum number, the higher energy. So let's talk about why quantized energy state matters so much in chemistry. Quantized energy state help explain why atom gives off specific color of light or atomic spectra. These fixed energy are key to quantum mechanics, which show us how tiny particles like electrons move and behave. For example, why fireworks explode. The different color come from electron jumping between energy levels. And this is not theory, it's had real-world impact. This concept is the foundation between lasers, solar panels, and even quantum computers.
All right, so now I just want to take a moment to kind of bring everything together, so kind of recap everything that we've learned throughout this lesson today. First and foremost, the particle in a box model is pretty simple overall, but it does reveal some really interesting information about the movement or tendencies of particles in space. So we use the Schrödinger equation to find wave functions. Wave functions are essentially going to be what we get from solving this equation. They're going to describe the particle's quantum state, but they're actually not something that we can measure outright. So it's not going to give us any physical information about the physical properties or location of a particle. However, what we can measure is the probability density, or the wave function squared. This value is going to tell us where we're most likely to find the particle in space, so it's going to give us a really good idea of the potential physical location of that particle. However, I always like to add that this measurement is done with uncertainty, so we never know for sure where exactly this particle is in space. The probability density is just going to give us, again, a really good idea or a sense of where we are really likely to find that particle. All right, thank you so much. I hope you learned a little bit about particle in a box, wave functions, probability density, all that good stuff throughout our lesson today. I hope you were following along with your guided notes, doing some practice problems, and reach out if you have any questions about anything. Thank you.